Okay, should be live here. Hi. We've got some research to do this week, and last week of cut for me as well. So minimal energy. I'm going to do what I can to get this block of work done. Let me talk a little bit about what I've been thinking about. So we have a whole bunch of experiments here. Hey Tim. Okay, so we have a whole bunch of experiments, right? But what's not happening cleanly is this is supposed to, you can kind of see it here a little bit, but we should be drawing this nice like exponential curve, and it's not doing that. Make your mic louder. I think I just have it too far away. Let me fix this. We'll try something like this, yeah? That ought to be loud enough. I think what I have to do here, there are a couple different pieces to this. First of all, yeah, so this is still up. It's suggesting experiments. Some of the suggestions are reasonable. Not all of them, though. In fact, a lot of them aren't very reasonable. Presumably because it's outside of the data support, right? I think if we just filter experiments outside of the max cost. Let's do that. Now we have a couple things that we have to do today then in that case. Okay. So we're on the right machine. So this is the problem, Tim. We have two cost variables now, right? We have samples and we have runtime. That's the issue. We have two of them. I think what we do here and do one frame skip. Wouldn't you just do 2 experiments? No, you wouldn't. Because that will get you the 2 endpoints, it doesn't get you the curve. But, to your point, that is actually what I'm doing now as a baseline. Is I'm going to do that slightly more rigorously than I did before. Hello, FBR. Hello, Aziz. Welcome. Right here, right? We do downsample 0 as well. Okay, so we have env num ends. So other than changing the network size, I think this is mostly what we want, right? The only other thing I can think of is I can technically mess up the mini batch size, right? The way 3.0 is structured. I want to fix the mini batch size. Let me see what it's doing for this. I got some pretty good results before, didn't I? Actually, can I do something real quick? Um, we're gonna try total time steps. Oops. Okay, so here Hmm. I can just fix it to 4096. I'm trying to think of a clean way to do this. Okay, so 64. This is fine. Let's just do this is at... I'm going to set this to 4096. Scott model. You just have a million things you're doing, eh? Not work on one thing. Yeah, I hear you. Here. Right, I need to do other one. Okay, I think that this is a quick hacky way to do this. Hello, Jess. These are not amazing hypers. That's very good, though. Okay. Okay, so this is done. Let me just double check. Didn't mess this up. I didn't. Perfect. See what this does. So that should be a sanity test on like pure sample F. Lol, yeah, enjoy your API key to your free logging app. You can go log some plots if you want on a public repo of plots. Very useful. Alright, so that's the super simple sanity test. Let's actually just have that up in a window for while I'm working on stuff today, just so we can monitor that. This should give us... Well, I mean, this isn't going to tell us anything until we filter, but we'll let it accumulate. Yeah, we'll let it accumulate some runs, right? On the other monitor. This one. Here. Welcome to all the YouTube folks. Maybe I should give a little bit of context about what we're doing here. Weston, I'm going to agree with you while simultaneously denying it's a real thing. Can I do that? In my mind, like, having the ability to just focus on some boring shit that you're not interested in for hours on end, like, that's, like, that should be the thing considered a disorder. Yeah. Alright, so... Let me give you a little bit of context, though, for what I'm doing here. Here are, I don't know, a couple thousand experiments of Pong. Each of these points represents a different experiment. The color of the point represents how good the run is. The dark blue ones are solves. And what we want to do... what's the thing? Epic Pen. I love how software nowadays takes 3 seconds to start. Alright, what we want to do is something like this. This line. Right? There should basically be a frontier where you can spend more compute or you can spend more data. And then the shape of this curve is really important, right? Because if the shape of this curve is like this, if it's a linear thing like this, then this means, like, you know, there's like this pretty clear trade-off between sim speed and compute. If the curve looks like this, It basically means that you always want to run this point here. You don't really need a ton of data. You don't need a ton of compute, or you need a ton of data, you need a ton of compute. Whatever it is, it's scale invariant. And then what we're expecting is that most things are going to look like this for the most part, where there's like an elbow. And then the points we're going to care about is like, we're going to care about this point, because if we have a fast sim, this is the fastest we can run our experiments. And then we probably care about this point, which is like, why is Riot opening? The heck? We probably care about this point over here as well, which is like the diminishing returns in either direction point, the elbow. Interested in RL. Yeah, but the thing is, Weston, like, you can be interested in the results of RL, but the thing is, the methodology by which research is done is like sitting at a desk typing shit into a terminal, and the moment to moment is not always super interesting, right? Like, do you ever literally lose the ability to focus on a game? League Env or Riot? Heh. There is, I mean, we do have a MOBA on the website. All the time? Really? That's actually impressive if you lose the ability, if you, like, can't focus on a game. That's, like, a whole nother category. Alright. So the main thing that I want to figure out today... Let me explain the problem with this, right? So, the default setup that we have for sweeps, it's designed to trade off score and cost, experiment runtime. But now we have two different costs, right? We have steps, and we have steps, and we have compute spend. Now I need to trade off both of these. And for whatever reason, this is now appearing to be difficult. I suppose I haven't really given this thing proper consideration, though. Those beautiful reinforcement learning experts. Welcome to stream. Got distracted. Alright, but that's like, that's doable, right? That makes sense. I've done stuff like that before, too. What is the fundamental of protein? Why does it work? Oh, well, because your muscles, you know, are directly made out of it. No, so the way that the algorithm works, there's an article on X. It's an improvement over carbs, which is the cost-aware Bayesian search. It's a Gaussian process that's estimating how long an experiment's going to take and what the score of an experiment's going to be. And it's using that to guide sampling, in my case, to cover the whole cost to score trade-off regime. It's trying to evaluate the Pareto optimal frontier. Now, the thing is, right, I'm trying to adapt it for two variables. I don't even know if this is the problem, though, to be fair. I think it's also quite likely that it's just the... It's pretty likely that just straight up the compute optimization, right? Like, the optimization to low data regime is fiddly. In which case, what should I do about that? I guess what I do is I do stuff in parallel, right? So I take... Let's take... This is our sanity, which is our slow implementation. And now let's go to our fast box. And let's see if we can do better on this box in pure sample efficiency under a maximum compute constraint. Let's do that. That sounds smart to me. So I can do that, Carlos, but then that's basically... So if you think about that for a second, that is exactly the same as just specifying a specific weighting between data and compute and optimizing one metric instead of two. What that misses here is that doesn't give you information about how the trade-off would go for sims of various speeds. Yeah, so Tim, that's the thing that I'm missing. I mean, I have benchmarks. I know for a fact that we can just, with our current algorithm and different tuning, we can get more than an order of magnitude in sample efficiency without even going crazy on cost. I know that for sure. And these, or would be a square in the bottom left. East. We've found some pretty good points, but we're not drawing the full curve. We found like some pretty dang good points, though, I will say. Diagnostics, yeah. Well, we have a few different things we can do for diagnostics. Like, making it artificially slow, right? Like, I can literally do the exact same thing. Just, like, all I have to do is if I make the score function log cost, like log time multiplied by log steps or something, I can do that trade-off, and it'll draw me a curve, but it's like it's not going to get the endpoints. Here, I'll show you what I have in mind for this at the moment. This thing. Okay, so here we have steps, uptime. Okay, so now we have our logs, right? We're going to increase this to, let's say, 64. Make sure it's really accurate. 8. 64 ought to be fine now. We'll try 64. Like a goodly number of steps. Yeah, so now all we have to do go to our multi-sweep. times and steps, right? So now we have this thing here. And so this should now be only optimizing steps. Oh yeah, there's one other thing I wanted to do before we do this, actually, that would be better. This is just going to take out the stupid predictions. Honestly, this might do something. Is this enough? I think we have everything with this, right? This is just a max cost. Why do you need to optimize? So you're correct that for any fixed environment, we have what we want. And that was the entire point of the design of Protein. The difficult thing about this is that we also need to do science in which we are able to draw predictions about slower environments, right, based on fast environments. Like, I can't do all of my research on a super slow environment, right, to, like, understand sample efficiency. What I want is I want to be able to do my research on a fast environment, even if I am optimizing sample F, and I want to be able to run tens of thousands of experiments and fit like really good scaling laws. We're gonna actually like I think when I'm running these experiments, provided they're stable, we're gonna start going through some of the papers, and I'll tell you all a little bit about like the the research inspiration for a little bit of this. There are 3 good papers associated with what I'm working on here. See if this does it. This will be setting a maximum compute budget as well of about 10 times what we normally spend. So with 10x the compute, it's really not 10x the compute, it's 10x the wall clock, because it's not compute optimal when you scale down, but with 10x the wall clock, same hardware, what can we do? Same code as well. Let's see if this is stable. No? I think I can do this easier, right? Make sure we get this right. We can go to papers. How's this happen? I'll figure it out. Take me a few more minutes than I thought, but then we'll get to papers. I'll have plenty of time today to do the lit review and monitor experiments. Pretty much as soon as we get these Pareto curves in a good spot, we are... Like, that's the only thing I'm not fully sure about. Once we have that working well, everything else is pretty straightforward. The heck? No, that's not good. That's really weird, isn't it? Ah, that's annoying. Well, we'll have to do... A little awkward. Whatever. $20 million. That's a wrong number. First of all, right? Alright, so... Yeah, this is super sketchy. Hang on. I have 20 million steps. Oh, because I'm dumb. Yeah, that's fine. Right, and we also need to do like this. This. Thoughts on Tinygrad? Cool library. It's gonna take them a couple years, you know, to they say it's gonna take them a couple years before they think they can be faster on NVIDIA hardware. So we're gonna see where they go with it. I don't agree with everything they do in the design from what I've seen, but like pretty much anything that's 15K lines is going to be better than anything that's 1.5 million. So we do this. That was hilarious. I mean, I gotta give the guy props. That was freaking hilarious. Not my style at all, but like, that was funny as hell. Guy's first instinct is to drop a fucking mixtape. Like, are you kidding me? That was pretty funny. All right, so we got our runs. My dashboard and the Neptune dashboard as well. Double checking of stuff. This is just gonna run super obnoxious stuff, yeah? Alright, well, this is doing something, so we'll watch what this does. Yeah, that was funny. I mean, whether I agree with, like, the specific technical decisions, we need more people just, like, doing crazy shit like this, right? Like, it's in some ways, it's, like, kind of boring to ask, can I make something twice as good, right? You have to be a little crazy to ask, can I make something 1,000 times as good? But surprisingly often the answer is yes. Yes, you actually can. All right, so let's start the research segment here, folks. I'll give you a little bit of context for this new project. This blog post, which has this paper, this later paper. Schumann on both of these? No, Schumann's on the later one. And then this one's like a smaller one, but it's kind of just a nice paper. This guy's kind of nuts, but it's like a really well done paper. And you're going to make the 1000x programmer? I mean, what do you think it is I'm doing, right? If you solve a problem 1000x better, by definition, all right, so 3 papers here, right? This was kind of the starting one. License out algos. There are examples of this, and it's worse than you could ever imagine. So, this is the original blog the blog post, okay? Where they were doing gradient noise analysis and trying to fit scaling laws. But they were doing it on RL at the time, right? RL at the time was kind of a mess. They did actually fit a little bit of stuff to Dodo, which was cool. And there's a much longer paper. I've read sections of this. I've never read the full paper. Even though in my mind I have this as like one of the most important things, I've still never read the full thing. There's also this, which is much more recent. Scaling laws work, OpenAI. It's kind of funny that they published this in 2023. But whatever. And then there's also this short little paper, which was kind of a hobby project for this guy, but it's actually really well done. And the fits were really clean, which was interesting. So we're going to take a look at these. Paper time. Okay, so this is focused on batch size scaling specifically, and they fit gradient noise scale as a law for this. Noise scale increases as loss decreases. Okay, so this gives you adaptive batch size, it says. I don't think that's the full picture, but we're going to go through all of this stuff. Minus, like, intros and shit. Atari Breakout Pareto Frontiers. Okay, so this is, like, almost the right thing, except this is compute cost and training time. This ignores the environment speed, right? This is like fixed M speed. This is like the theoretical gradient mess thing. We ignore this. This is good. When batch size is very small, approximation has very high variance. So this is just gradient noise. By contrast, when batch size is very large, batch gradient will almost exactly match the true gradient. There is, when you're doing PPO, there's an additional off-policyness thing that's not that's a conflating variable here, but as a first order, this is fine. Okay, this is just background saying you can do gradient descent, right? Like this, all this is saying is if we're doing gradient descent, we're approximating the true loss using a fixed number of samples, and you can estimate the variance of this gradient. You can estimate the variance of the gradient, right? This is all the theoretical stuff, where it's saying that you should get perfect scaling. So you should just be able to increase batch size up to a point, and then it becomes ineffective. That's the prediction. Again, in the real world, this is modulo learning rate and data staleness and a whole bunch of other things. At least in RL. It's a lot easier in supervised. Everything's easier in supervised learning. Predictions for data and time efficiency trade-off. This we don't have to care too much about. We mostly care in the experiments. Okay, so here, yeah, learning rate tuning is important. Expected patterns in noise scale, larger for difficult tasks. This is true. Growth over training. This is also usually true. Well, it depends, but usually true. Weak dependence on model size. Number of model parameters in the neural networks cancels in the noise scale. We do not expect B to exhibit a strong dependence on model size at fixed loss. Models that achieve better loss will tend to have a higher noise scale. Okay, so for a fixed level of performance, you don't actually expect to have to change the batch size because you change your model size. This is their prediction. Trade-off between speed and efficiency is controlled by the batch size following this form. The critical batch size can be predicted at the order of magnitude level by measuring gradient noise scale. Noise scale can vary significantly. Okay, so this is a fit. I don't know if this is a crazy useful fit necessarily, but this tells us something at the very least. Critical batch size. For it varies a lot by problem complexity. A lot of these, and this is actually mini batch size, not batch size. So this is saying that the mini batch size can get into the tens of thousands, which is a fit with, and this is a fit with what we've done. This is also not exactly correct because they're using here, they're saying batch size for Dota team, lower bound, but this is not correct because this is a mini batch size. I mean, other way around. This is a full batch size when what you need is the mini batch size. Optimal learning rate is displayed for a range of batch sizes. This is again supervised learning. So linear, right? If it's log and log, then it's linear. Up to a point, and then it falls off. So it's mostly proportional. So if we were to fit a bunch of these laws, we could reduce the number of hyperparameters a ton. Larger batches are fastest. Large batches are fastest. Small batches are more efficient. And this is like 2 orders of magnitude as well. But this is in optimization steps. So they're measuring what's not quite the right thing. Batch minis, batch just scaled with higher params. No, not at all. That doesn't, adding more parameters really doesn't make much of a difference. That's not the main dependence. So, I mean, this is like a decent fit. It's like off, but there's also classification. We need RL. Okay, so we want to see the Atari results. Noise does not depend on model size. We need the appendices for this, though. We have this estimate thing. We roll out the environments 5 steps at a time. What? Vary batch size by varying number of environments running in parallel. We randomly step each parallel environment. Okay, so I don't think they fully like controlled for everything I'd want to see here. I really mainly just wanted to see some of the results I haven't looked at in the appendix though before. Examples processed, optimization steps. This is kind of a good one, right? Because this tells you, here's breakout. Okay, so this actually is only, right, this is like maybe a factor of what? A 5 maybe? Yeah, maybe this is like a factor of 5 that they get here in difference at the optimal. Though if you go to here, it's like a factor of an order of magnitude like 10. So the shape of this frontier is actually kind of important. It's like the fact that it's shallower up there is not necessarily good. So it seems problem dependent because for Pong, look at this. So this one here is shallow. And then this one here is steep. We have for Dota. And we just have these fronts for like a bunch of the different Atari M's. They do have different shapes, which is interesting, right? Different curvature. Because here, this is like order of magnitude difference in compute. Or not, was it in examples? This is our sample efficiency order of magnitude. And here, this is the concerning bit to me, right? So like, for the really big problem, like the really big problem, it's very flat. Which means you just need data. We'll see whether our results match this. This is a bad thing for us, though. We don't care about classification other than, okay, these are easy tasks. Okay, so the variable batching thing, right? Ah, this is an important bit. So when the batch sizes get too big, it seems that like determinizing training is bad. This I've seen as well. Okay. This is basically everything we wanted to get out of this one. There are some laws we can fit to batch size, learning rate. That would couple two of the parameters a little bit. Learning rate's also dependent on model size, though. That's MUP. But for now, we know that this exists. We have the result that for some M's, there's a huge difference in sample F. And we also do know that, like, it's possible the more complex M's, this is not going to be as good. We will see. Let's go take a look at our results real quick. Okay. Running more experiments. It will take a while, but we're getting results. This one. Why does this not work? Hello? What the heck? It's running a bunch of stuff. And it's like not full solving, which is weird. Yeah, it's not full solving, which is really weird. Keep going for a bit. Oop. Okay. This is the big paper. I don't want to do this one first because this one will be quick. This is like scaling laws stuff for X. This is an ELO-based system. Okay, so this is difficulty is exponential. This is reasonable. Equal to RL guide should be tips on interpreting graphs and logs. Yeah, the thing is, it's harder to make a guide on that because that's just like I've been doing it since I was 16 and it was hard type of a thing. I mean, arguably earlier, depending on where you count. We're getting very close to it having been half my life on research. Kilo versus perfect play. Training run of each differently sized agent follows a sigmoid, starting from random play and progressing to some plateau. And you get a basically pure exponential fit. But are these different graphs? Let's see. But this is just saying that, like, task difficulties scales predictably, right? This one's kind of cool because you get scaling for search. Wait, so it's just batching, pairing. No, I mean it's been almost half of my life so far. I mean, the only thing that's interesting, I think, here, and I don't even know if this is interesting because it's like it's a search-based method. Okay. This is not what I remembered it being. Clemens. Anybody else on here I know? Funny. Okay, so this is good scaling work, but not on the area that I wanted. This is like if you happen to have a problem of this form. So it's really just going to be these two are the important ones. Look at the experiments again. Was this where I had them? I think so, right? Right here. Interesting. Not really full solving, is it? Keep going for a bit on this. I want to at least get through this paper. 30, we got time. Cross entropy loss improve smoothly with model size and training computer. Minimum compute required to achieve a given return. Intrinsic performance scales as a power law. Minimum compute required to achieve the return. Let's see what they found here. Compute parameters. Wait. Intrinsic performance. Compute flops, mean episode return. Wait, why is this? Why don't these keep going? They kind of cut the curves at the weird spot, didn't they? Like if we take one of these, 10 to the 6, 10 million. Okay, we need to get we need to start reading this stuff. There's no cross entropy. The usual objective mean episode return need not scale so smoothly. The model size that achieves the minimum test loss for a given the model size that achieves the minimum test loss for a given compute budget. Like a performance metric that behaves like test loss. Scalable model family is a collection of models trained in a uniform way, parameterized by model size and the total compute used in training. Intrinsic performance of an arbitrary policy is the minimum compute required to train a model of any size in the family to reach the same return. Intrinsic performance scales approximately as a power law with model parameters n, environment interactions e. Model parameters n and environment interactions e. The number of interactions is not bottlenecked. I scales is a power law in N. The model size is not bottleneck. I scales is a power law in E. Wait, so when... What does this mean? Optimal model... Okay, here. Optimal model size scales is a power law in that compute budget. Assume training compute is proportional to NE, parameters times interactions. For a given compute budget, there's a trade-off between N and E. The optimal value of N scales as a power law in the compute budget. What, Jess? So the number of model parameters oh, now we're good for a bit, is proportional to the compute to something. ProcGen, Dota, and MNIST. We would not expect our qualitative results to change much. Quantitative results such as scaling, I suppose, dependent on the well-tuned hypers. 1 over square root of width. Okay, so fitted values of coefficients. Considered a fit. Look like a fit. Well, these look way better. Parameters and compute. Optimal model size versus compute for all of our experiments. And this is saying if you double your compute, you should double your... Well, I mean, I guess it depends on the slope of the line, right? But... I mean, they're not that far off of 1. Double model size, double compute. Yeah, but generative modeling, right, is way up here. Like 3 orders of magnitude difference. And it looks like the harder M's even. The harder M's scale with more data, right? Which is kind of funny. That would actually be consistent with the other paper, right? The harder M's scaling more heavily with data. I mean, there are some questions I have from this. Yeah, this is a log fit. This is telling us we should just be able to increase model size. I've never seen that happen. Never. So why not? Right? Interesting. Flops per forward pass, huh? So, I mean, this is just saying you leverage the compute and magically is better. Lower model is the better. I've never seen this work. So I want to know why. Okay, this one's cool, right? So this one is saying interactions This is a big difference, right? Because this is an unsolved task, so this is kind of different, right? Because if you keep drawing this line out, this is what we want to be able to have. We'd love to be able to have, like, this level of scaling. Yeah, this is a key result. Okay, I've not looked at the full appendix of this, I don't think. But there are only certain bits of this I care about. $32 mini batches. Oh, perfect. Learning curves is a result. Yeah, so there is an optimal model size, it seems. Okay, so these ones, well, it's this. Am I reading this differently? Because it's not the case then, right? So if you're spending a specific number of flops, there is an optimal model size, right, for a specific number of flops. Yeah, right, like, okay. The more flops you spend, the bigger the model size is, but for any fixed budget, there is an optimal size. And then this one up top, this square with it, Yes, because this one is just straight model size, right? You're gonna spend, like, this is 3 orders of magnitude of compute. Like 10 to the 5, where is this? Up here. You can spend 100x the compute. I mean, realistically, if you get to this 6th one, which is like down here or whatever, you can extend this out 10x. Okay. We definitely want to reproduce, though, this model size scaling thing. I have not found this to be the case yet. How can I have not found this to be the case, right? Are the tasks just too easy? For any fixed for any fixed amount of compute you're going to spend, there is an optimal model size. Okay, hang on. So if we're going to spend, but our implementation's really, really efficient, right? So it could be that the optimal model size for the compute range we're spending is just really low. Because you solve the task at some point, right? So that optimal scaling, I suppose it depends on what you are fixing. So if we fix the number of environment interactions, we might get a different result. Certainly it's supposed to be the case, right, that if we can't solve it with a super low number of environment interactions, increasing the model size is supposed to help. But I think I've just been screwing up with stuff because, like, when you already have the environment solved, it's not the case that increasing the model size lets you solve it faster in wall clock necessarily, right? It should always, under optimal hypers, it should always help with samples. Okay, so at least I have some understanding now of what I've been screwing up. This thing is wonky. It is interesting to me here, though, that, like, this seems like it's massively improved the sweep efficiency, right? So maybe this has actually been a big improvement, completely separate from what I'm looking at and caring about, but still. I'm trying to think what the smart way is to handle this. Okay, well, I mean, here's one thing we can do, right? Let's do something super basic. Okay, we got 12 million steps, right? Let's also change evals, just to make sure we don't screw this up. Okay, 128 eval. Okay, so that is a solve in 12 million steps. It says 45 because that's from eval. If I reduce this, let's say we're only going to give it 5 million steps, right? Ah. So there is actually a, interesting. Well, that's kind of awkward. Let's give it 2 million steps. It learns much. Yeah, I'm wondering if this is going to jump. Okay, no. Now, if I just do... We have to cut the learning rate in half, I believe. This does not help, right? This is still very, very bad. I'm going to give this one other chance here. It is quite possible. Well, can I just change the batch size without screwing with the mini batch? I think I can, right? Let's just do this. Get more unique data. Yeah, never mind. That doesn't help at all. So we don't get the scaling result at all. And this is consistent with what I've seen previously. So why don't we? We may as well try it on a slightly harder environment. Batch to no mini batch. What? What does that do? This is super slow for some reason, but whatever. I'm not looking at time here. Yeah, this is our baseline, right? Yeah, I've been meaning to address that, Jess, but it's not like obviously, oh, just change it to X and it's good. Like, I gotta change several things. Okay, so this is with 10 million steps. $11 score. Then I'm supposed to be able to do and then I'm doubling, I'm quadrupling. Oh, wait. Let me just go double check. Let me make sure I'm scaling the learning rate correctly. Proportional to 1 over square root of width. 1 over square root of width, right? So this means that if I quadruple the net size... Wait, atom learning rate proportional... Wait, is it supposed to increase? We'll try both. We'll just try both. Go. Okay, so this is worse. Right, this is just worse. And then we'll try doubling it. It is possible I got it backwards. I didn't think so, though. That's kind of weird. Oh, no, because 1 over square root of width, right? So yeah, it should be totally wrong to double it. But we'll do it anyways. Larger nets need smaller learning rates, right? And of course that works better. We have to compare to the baseline of just running the smaller network with larger learning rate. $22, $13, and $22. Okay, so like no observable effect. Isn't that weird? Like that's weird, right? Why haven't I seen? I mean, this is an effect that's been documented several times, and I've never seen it in the whole course of. Well, I mean, I guess I've seen it on like some of the harder ends needing bigger models. Pretty weird though. Definitely pretty weird. I wonder if it's like some wonky initialization thing. It really shouldn't be, right? There should be like a very clear difference. We gave it 100x the number of parameters. I mean, everything else I can think of relies on tuning, right? I wonder if it's like architecture and like, domain specifics dependent. I wonder if it's like the pixel encoder, for instance, benefits from the parameters or something weird like that. They did it in Dota though, which is state. But Dota's is hard enough problem. Mm-hmm. That's super irritating. Regardless, I think we've at least found like one really good thing today, which is the max cost clipping thing is like really good. Like literally just clipping max cost. We could even clip like max steps or something. That's really useful. This is 2 million, yeah. Okay, I'm trying to think what else we can figure out with this. So problems that we have. We've got relatively good sweeps for wall clock. We can try this modification in isolation for that. I know we could go like add in max cost and stuff. That's actually not even a bad idea. Go add in max cost. We could test that in isolation versus this thing. Honestly, a pretty good thing to do. And see what type of stuff we get out of our sweep, yeah? Kind of down to do that. This is uptime. Do you need to use Unity? No, you do not at all. In fact, if you do that, it is guaranteed that your environment will be borderline unusably slow. Alright, so this is fine. Anything that needs to change? I don't think literally anything needs to change here, right? We're just good. Right? Oh, yeah, there's one. We need to do the max cost filtering. What would you recommend for max obs? Like maximum observation size? I think we have 1.7 kilobytes. We get up to 500,000 steps per second, 20% overhead. I mean, if you can keep it in hundreds of bytes, it's good. If you can get low thousands, it's okay. If it's like 10 KB, it's too big. Yeah, 300 KB is way too big. You're screwed. Oh, I just saw your message, Jess. Yeah, Windows is not fun. Bad. I wanted 64 by 64 by... What is this? Is this a render? That's 16 KB, man. It's not 300. Where did you get 300 from? If you're doing this in floats when you have pixels, you're trolling. So presumably these are unsigned chars, right? No? No what? Float between -1 and 1 for pixel data? What are you doing? Why do you have 4 channels for pixel? Like, why do you have 4 channels then? Explain your obs. I'll be back in a minute. The restroom and take a little walk around. Pixel values. Checking simulated pixel values. Then why, if those are simulated pixel values, if you're doing RGBA, why are you representing it as a float? And first of all, representing it as a float, that's a multiple of 4, so that's 64 KB, which is too big, but it's still not the 300 KB that you said. And like, why aren't you doing... I guess it doesn't need to be. But wait, if you need... I don't know. I guess technically... No, you should totally be able to just put it into a char. Yeah, you should totally be able to put it into a char. There's no reason not to. You're losing a negligible amount of precision. Okay, here's our new sweep thing. This is... Well, we'll see what this does. If this makes a difference or not. Could technically filter by max score as well. Might it be useful? The 128 by 128 with this would give you 256 KB. Keep your data concise. Best you can. Alright, so this distributed thing is just like not doing it, it seems. Like at all. This thing is actually kind of interesting, right? Because... Oh, because this is E7, so this is 20 mil, right? Right, because this is just supposed to be fast. Yeah, so this is just supposed to get this down to like whatever seconds. Okay. We really wanted to just know the stability of this, so that's not a big deal. We got 32 runs this so far. Down to 1.6 mil. I believe this is with no frame skip as well. That is... Why is this sweep like so much easier to learn? Probably because this max cutoff thing. Right? Because like technically... These guys... Yeah, these guys probably are barely getting filtered. What do we do from here? We found one very silly thing with protein. Probably from the kernel, frankly, isn't it? Linear kernel. We can think about the model scaling thing. There are a few different axes here, right? Like, Presumably, batch size scaling, reducing num-ems in batch size, and retuning hypers, we can get quite a bit more efficient. Model size thing is weird, though. I honestly don't have a good explanation for that, right? Like, why is it that... But, like colloquially, this is a pretty commonly reported thing. We have a couple papers that have these nicely fit scaling laws that I haven't really ever seen it in almost anywhere. Depending on, like, there are a few environments where you do see it. Definitely not across the board. What do we do with this? Well, one way or another, this like silly little fix has definitely improved the sweep algorithm. That's a funny thing to have missed. Like, yeah, this here, for instance, this one here. Yeah, this is a solve, actually, right? This is like 20. And this is only this is 10 million steps, right? Because this is supposed to be the speed one. That's fine. And we've got like this thing here with all these fancy curves. This axis is different, right? This is the 1e6. Wait, 1e7, huh? I thought this was supposed to be the sample F1. Weird. Breakout or something? Why the heck is this going to E8? Oh, because this is totally different. Cool. The heck is this then? This is something else. Yeah, you just have too much data then. I don't know what you expect to learn over that space. Like, you literally have 10 KB obs for Dota. Doesn't need that much information. What the heck even is this supposed to be? This is Pong. How the heck is it out here with E8s? And what is... what is going on here as well? Really? Yeah, this is the right one. Is something. Super annoying. So this just produces a ton of really shitty runs, apparently. For some dumb reason. Yeah, this is awful. Hey, something, welcome. Yeah, I'm on research. I'm on the next research block. Research is hard, as usual. Trying to do large-scale hyperparam tuning. And we're gonna try, we're trying to fit a bunch of scaling law type stuff. I guess I probably jumped the gun with a lot of this, huh? Hey, this is kind of nice at the very least, right? Way quicker. So then, do I just try to like... I guess, do we try to like retrofit this onto it's so annoying when I do this, and it's like I try to do too much at once and I screw up, and now I have to go back and retrofit everything again. I think I just have to do it though, right? I think basically I have to separate out in my head the multi-sweep stuff from the sample efficiency stuff, right? So we go do like pure... Maybe we go do like pure sample F. We do pure multi-sweep. And standalone multi-sweep is already pretty dang good. I guess we gotta do that. I know I gotta do it, it just annoys the hell out of me. It like pisses me off that I still mess stuff up at this level. Hey, research is hard. You have to be like, however careful I am, it's like I always have to be way more careful. Kinda nuts. Yeah, it's annoying. It is real annoying though, right? I don't necessarily want to see like electively swapping out limbs. We don't have to have like cyberpunk shit future, right? See, my version of the sci-fi future has like, nanowire augmented muscles and whatever the hell that let us all deadlift 2,000 pounds and like sprint for hours on end. Well, I mean, you're not a helpless sheep, right? If you want the technological version of, if you want like future tech to be cool and not shitty and dumb, then build tech that's cool and not shitty and dumb, right? Roko's Basilisk is bullshit, is what that is. I don't put much stock in mediocre philosophy. Build cool shit. That's all there is to it. It's really not any more complicated than that. I mean, like, AI is definitely gonna happen. It's just a question of whether the current, like, really dumb language model thing gets there or not. You know, can we scale the completely dumb thing until it's better than us in all meaningful ways? Or does the thing pitter out in ways that really matter? Is what seems to be happening at the moment. Oops. On the do anything. We shall see. Oh yeah, I didn't do the multi-suggestion bit, yeah? Fix that. Welcome, Georgie. I mean, I agree it's a part, though not for those reasons. Um, so the parallelism that we use, Georgie, it's just a big block of shared memory accessible on the main thread, where all the M's are just dumping their chunks of data into that. Slices of that still have to get synced to the GPU. There's no CPU to GPU async buffering. It's only CPU multi-core buffering. Multi-stage buffering to GPU is something I want to play with, but I don't want to bother until 3.14 because Python gets threading and that makes my life easier. At least when they have the full official threading stuff in it. The groundbreaking work of today, or the attempted groundbreaking work of today, is high performance hyperparameter tuning across the frontier, if you will, of like the compute data trade-off frontier. So can you spend more compute on a problem versus more data, understanding that trade-off very clearly? The current problems I'm having are that we have to adapt the hyperparameter sweep to be way higher throughput and to do multi-GPU. We have to adapt the hyperparameter range over which we're tuning to support sample efficiency, which also requires changes to the trainer. And then we also have like new visualization infrastructure for all of the new experiments. And then getting all three of these things to be correct without messing up anything is quite tricky. That is what I'm doing. Hello, Yappuccino. Super impressed with your stamina. Man, my stamina right now sucks. Like, I want to be doing 12, 14-hour engineering and research days. This is the last week of an utterly psychotic 1,500 calorie a day cut. So, when I'm also running 10K in the morning and lifting decently heavy as well, I have no energy at all. I'm trying to mostly just get through this week. If I'm hitting my goal by the end of it, then I will be done with this block. I'll be able to start on more serious research. Though in practicality, I probably have a few things to polish up in California and head back. So it's probably not going to be until I get to Maryland that we get into like really serious stuff. I get to spend like a few months of kind of like monk mode, work on farm on hard research. See how that goes. I do not run 20 miles most of the time. It's actually been quite a while since I've ran 20. Most I've ran this summer is 15, 16, something like that. The course is hard, though. Take subs for focusing. I mean, let's say that 98% of the time, just coffee. And nothing on the exercise side. Like, realistically, the way I get all my stuff done right is like, I get obsessed with a problem, I work on it a lot for 3 or 4 weeks, and then I burn myself out and I like, have a few weeks where I'm less productive, and then I like come up with the next thing to work on. So it's kind of like it works in cycles. Honestly, the thing I've always been trying to figure out is how I can have it be more consistent, but I've never been able to do that. But hey, stuff gets done either way, right? So I'm hesitant to screw with the engine of progress too much. Of course, there's parallelism. Excuse me. What the heck? I hate GitHub sometimes. Dude, what? No, this is correct. Huh? Why did it require me to authenticate twice? All right. So the problem is basically if you have your multiprocessing method in Python, it literally doesn't matter what the hell you do because like using any of the wrapped C primitives in Python, there's so much overhead that you won't be fast enough. Like the puffer architecture is basically the only architecture that makes sense in if you want Python compatibility. The only thing I could do that would be potentially faster, right, would be to make a custom backend for our C environments that's separate. But like that's usually not the bottleneck. But honestly, I hate the token thing, right? If they want to force 2FA, force 2FA. But forcing like this token thing is just bullshit. All right, so we have multi-sweep. Let's go to... Go here. You're not rewriting Torch. Is the thing. I think literally the only thing that I need, like I actually need, is Torch. And the thing is, they have a C++ API, but it sucks anyways. So like, Python to C++ is not even an upgrade in my mind. Python to like nice C would be an upgrade. I really do not like C++. Kinda ass. I do so wish that Torch had gone with like nice minimal close to CUDA. Well, you technically have CUDA C++, but like Torch is very C++. Alright, we'll see if I've done this correctly. This Yaxine, who is this? Heh. This is cute. Fun Raylib. Okay, so we actually have this thing running. Cool. So now I should be able to just go... I just copy the damn file. Just gonna copy the damn file. It's so weird. I'm like actually too hungry to think straight. And, like my stomach is rumbling and stuff, but it's like not even it's not like, oh, I want to go get food. It's just I just feel tired. No idea why that is, but yeah. One more week. Is it smart to learn Jax for RL? For environments, no, it's a total nerd snipe. It's both harder and slower than writing M's in the way that we write them around here. A fun exercise for one of my contributors would be to port any of the Jax environments to C and watch them be 10x faster. What is this having to do with data serialization? What I'm doing here? Nothing in particular. Why do you ask? Does it actually use weight free? Wait, what? Oh, you're asking Georgie. Don't challenge me to make more M's. But for training Jax is very interesting. Um, not really. What is interesting if you're ignoring if your environments are not in Jax, what is interesting about Jax for training? Oh, the guy in the chat is he's just talking about his own stuff. That's Georgie. Yeah, that's just Georgie being Georgie. How do you summarize what you're up to today or in general? In general, we do high performance reinforcement learning, research, applications, generally just trying to make reinforcement learning as a field be fast and sane. Whole project around PufferLib is dedicated to that. It's all open source. Today in particular, I am working on high performance hyperparameter tuning. I'm working on attempting to expand my current hyperparameter tuning setup to track not just performance versus cost of performance, but having like data efficiency and time efficiency as separate metrics. I'm working on visualizations so that once I make that work, I'll be able to queue up like thousands of experiments to do large scale analysis. This is like a science at scale, I suppose, portion of the Puffer arc. That's what I'm doing. Do you think the Jack stuff is not long term? Well, it's just a super janky library, right? Where the code sucks. If you've read any Jax code, it's like awful stupid code. Um, it's not like all the companies are using Jax either. You can get MFU good with PyTorch just as well. PyTorch isn't amazing, but it's a hell of a lot easier to work with than Jax. Like, basically, Jax only makes sense if you're Google and your researchers have a billion engineers they can bother when everything breaks. Like, every single time I've gone through Jax of any type, I've regretted it. And like, yeah, Google is super smug about it, but Google's super smug about everything. Like, especially given that you can't even buy your own TPUs, right? Like, okay, if you could buy your own TPUs, then maybe. But it's like, oh, rent our TPUs and then use our language without our internal support on it. No. I guess, like, longer term, the thing I would want out of a learning library doesn't look anything like Jax. So, no, it's not a lot faster than PyTorch. PyTorch has compile. You can do the same thing. That was what the community is going towards. Yeah, but the community is, like, completely stupid. So what does that matter? Like, the RL community is kamikaze their own field. Okay, finally, here's something. Okay, so we should not be getting data points way the hell out here. Something's wrong with this. What the hell? I don't know why this is 2E8. Do 1E5. Oh, you know what? I know why. This is actually fine. This is totally fine. Leave it alone. Nicholas, I'm not, like, just being arrogant or exaggerating either. Like, just side by side the code for one of our environments with, like, some of the better Jax code out there. You'll see our code is shorter, easier to read, and 10 times faster. And it doesn't chew up your GPU time to do it. I'll be right back. Let me use the restroom. Let us see. This does. Okay, can we get us cost score trade-off instead? For Marl, nope. It's not somehow better than PyTorch for RL in terms of speed, because PufferLib is faster by a lot than any of the JAX libraries. And PufferLib, only the environments are in C. Like the rest of PufferLib is just Python. And I guarantee you that our C environment code is way easier than the JAX environment code. It's literally, man, it's just stupid researchers like wanting to write something that looks familiar, so they come up with like the most convoluted domain-specific language that looks kind of Python-y instead of using literally anything else. That's all there is to it. Yeah, so this is like a ton of experiments. Here. Oh yeah, Nick. Here. Here's probably like the craziest multi-agent thing out there, right? So this is Neural MMO3. This is a 1,000 agent environment. We've trained this on 12,000 years of data, like 650 billion observations on one server. Environment is one file in C. The training is all Puffer standard PyTorch. You have some sort of repeated normal from game. Repeated normal form, just a matrix. Any basic environment like that, you can write in a couple hundred lines. Like, we have a pretty clear-cut guide on this as well. Like, this is, if you haven't written low-level code before, people bounce off, but, like, it's really not that hard. Here, I'll show you. Okay, so this is multi-agent snake. I'll show you that one. This is, like, one of the first environments I wrote. I could make it way better if I were to write it now. So this is snake. It's, like, I think less than 300-ish lines of code. This is data. Close the environment. Here's your observation function. This is all you have to do to compute observations. You get to write loops. It's really simple because loops are fast in C. Here's how you remove an agent from the environment. Here's how you spawn an agent. Here's how you spawn food. Here's the reset function. Here's the environment dynamics, the step function. And then all this is just the rendering. And that's it. Like 300 lines of actual code, a little bit of boilerplate at the top. And that's Snake. And then you can go to the website and you can watch our agent play Snake. Where is it? You can just watch the agents play Snake. You see? Okay, interestingly, these scores seem... There are a lot of good scores in here. What's going on? Yep, everything else is in that. I don't know why you would want a custom variant of DQN, though. We have a much nicer training algorithm. Like, DQN's a very bad algo. Oh, I know why this is. This is me being silly. Analytical proof. Yeah, so you would modify our trainer. Our trainer is like more complicated, obviously, than something like CleanRL. But it's simpler than one of the big bulky modular libraries because the trainer's one file. But it's like very high performance, right? I mean, PufferLib trains millions of steps per second. That's kind of the whole shtick with Puffer, right? It's just fast. Works. Okay, I mean, so this looks good, right, to me? Like, this is actually pretty solid. So can I run this exact same thing? I wonder if I can now run this exact same thing. And... this. There we are. I do need to change one thing here. M's are not your typical M, they're more like molecular dynamics. Here's into the whole thing. Welcome, Carlos. Molecular dynamics RL is pretty awesome. Actually, like, material science type stuff is one of the top things I want to do with Puffer. How is Jax convenient, though? Like, it's not, right? You have to do everything as a set of array operations. You can't just write arbitrary loops and conditionals like you would want to. Is it actually a compute-intense environment, do you know? Like, there's really not that much stuff that needs to be on GPU. I mean, like, literally just, if you just side-by-side Puffer environment code, Jax environment code, Puffer training code, Jax training code, you'll see the difference. Yeah, so molecular dynamics, I agree, at least portions of that are very well suited. So yeah, I'd have to do CUDA most likely. But the thing is, that wouldn't even bother me, right? Because, like, how I would do it is I'd make it so the code would run in C, or it would run in CUDA, because CUDA is literally just C. Yeah, but scaling to 100k agents isn't a problem, though, because, like, throughput's going to be measured in agent steps per second. It shouldn't be that. It actually should be the opposite. Typically, a lot of things, like, there are a lot of algorithms that, when you get to large numbers of agents, there are a lot of checks that you can technically do in better than quadratic, but you have to do them quadratic on a GPU. So actually, technically, Puffer's faster for small numbers of agents anyways per sim. I don't know. Puffer should just be fast. Puffer always fast. Is a good library, sir. Speed. Dude, Jax is 12 to 15x faster than your C++. Aid. This? Is this it? Which one? Where do I look? Damn, the site doesn't. Oh, now it loads. Their GitHub on this? Is there a source? In my mind, writing CUDA is actually easier than writing JAX for reference. And way more flexible. GitHub. Oh, is this your repo? Do you know what, like, training steps per second? Like, do you have metrics on how fast you're training? Puffer is currently with an optimized sim, is like up to 5 million steps a second. Typically like between 3 and 4 on a 5090. Oh, this is different? Okay. Oh yeah, totally different thing. Yeah, my bad. GitLab. I haven't seen GitLab in a long time. Code. Like the worst website ever. GitLab is just awful. Where the hell's the code? Nope. It's always so hard for me to tell if C++ is optimized or not. I mean, I will give you that, like, molecular sim is a textbook GPU Excel problem. I still wouldn't want JAX, like, ever. The thing is, like, so basically the way stuff is written in Puffer, you can almost copy paste Puffer environment code into CUDA and just run it. Because, like, it's just it's static C, which is basically CUDA. There are, like, very few changes you'd even have to make. Does that make sense? Like, we have not ever had to do this because our environments that we do typically are pretty low compute intensity when they're done in just, like, simple low-level code. But it's not like we can't do it, right? And I would still do that over having to deal with JAX. JAX dem, yeah. Well, you should definitely log your like training steps per second to see if you get anywhere near Puffer. Like, to be fair, if you're a systems engineer, it's possible you make stuff that fast, but like pretty tough. Like, Puffer actually can be made even faster than it is now, but like there are a lot of optimizations in it that people typically miss. Wait, where's the code? This is all like placeholder. This is like all placeholder, isn't it? Oh, here's some stuff. What is this for? Is this like, this is straight material science? Like, what do you work on with this stuff? Why is Jax used over CUDA? What's the appeal? People think CUDA's scary. It's not. I'd way rather write CUDA than Jax. It's like literally just researchers not having cis background. Vast majority, at least. Granular materials and swarm robotics. That's quite a mix. The swarm stuff, we have some fun demos around. We've got like our drone swarm M's and whatnot. At least this is working way better than before. CP Swarm Lab. Yeah, there's a guy from there, I do. Okay, I mean, this is at least considerable progress, right? So I think that before I think I didn't have this with no frame skip. Possibly now it's going to be quite different, though it shouldn't be more than 4 mil for a solve? Maybe 4 mil for a solve. Wouldn't be bad, though. Email back asking postcode on my GitHub and got ignored. That's obnoxious. You can keep emailing people. This is super fast at the very least, right? I mean, we've definitely fixed the... We have, like, performant hypersweeps, which is pretty friggin' awesome. Like, we've gotten this component to be good, I would say. At least good enough, for sure. Got cost pruned too. Got cost pruned. This is also without allowing larger networks and a bunch of other shit. Hey, Bet, how's it going? Yeah, wrong one. So... Trying to think from here. What do we do? Heh. Good luck with that, Bet. That's funny. Clearly, I'm competent based on my X profile. So I have a group chat that's like half Prime guys, and they mostly just post like horny bait all day. Okay. If they want their brand to be the horny tech bros, then sure. Some of their, like, the decentralized stuff was pretty cool. It's super funny, though. Talent would not. I mean, they don't do the type of RL that I do. That's funny. You have yourself listed as puffer, proselyte, and contributor. And support and all the other shit that you do around here. I've hardly any of that stuff. That's funny. Well, and I wouldn't be surprised, bet like some of their employees really don't have much experience. I mean, they seem cool, but it's not like a, I wouldn't be surprised if you get an offer. I don't know if they've actually raised, like, a decent amount or not, but... Current project. Search list chess. Flip frack. Head puffer. Head puffer Joseph Suarez. Where are you posting all this stuff from? But yeah, that is all our, that is like all the stuff. The Pokemon RL stuff was very good. That project would have been so much less of a pain in the ass if the end were just fast though, you know? Oh, I messed this up way bad with this frame skip, didn't I? Shit. It's a bit of a... No, I didn't. Okay, that's fine. I guess we leave it... Is there an email to reach you at? jsuarez@puffer.ai. Oh, for Bet? I don't know if he has his. Oh, not finding, it's found 4 mil. It's not finding, like, the 1 mils, though. Running a Flask server. I'm just forwarding a port so I can do, my own plotting, right, without having to copy the data to my local constantly. I'm not manually running a Flask server. It's just what Dash has. It's just shitty Dash, man. It's like the least bad of the bad plotting libraries. Okay, so this thing definitely made a difference, right? It's tough to say with the... Yeah. It's tough to say with the times. It's like 10 seconds, though. 8 seconds. Yeah, so presumably, this box is super slow compared to the other one as well. I mean, that's something, right? And then this one here. This was the super long one, no? I mean, either way. We have our sweeps. I mean, what am I expecting out of it? Is it supposed to be... Expecting, like, this frontier to be better, no? Well, hang on. No, I'm not expecting that because I didn't. Obviously, dumbass. Okay. I shouldn't be expecting that. I'm fine. This is totally fine. We're good. We've actually been making some decent progress, I'd say, today. You get the number of ends. Yeah, this will be decent enough, right? We can go from this and we'll see if there's any change. Probably need to check a few things here though, right? Oops. I messed that up. Hang on. Oh, I got Isaac running as demonic. Was it really that hard? Its own container. Fun. Let me know if you got my email. Uh, I'm not a great person to ask about that, but no, I think you should be fine. Not what I do. Okay, so this gives us this should be giving us at least the ability to potentially do a little better. We're not expecting this to do amazing yet though, right? This should be like a nice sort of midpoint type experiment. That one's new, isn't it? 3.5. Yeah, I think that's a new point. This is a new best point. This is good. Okay, so I mean, this thing can run for a bit, right? We're not sweeping model size yet or anything. I can go make that change real quick. It's not hard. What the heck is this? In here? I think it's in here, right? Load policy? Yeah, here it is. Let's see. Do it like this. Alright, cool. So now all I gotta do is... Okay, well, we got this version in now, right? Let's see, first of all, have we done anything? Whoops. Have we done anything amazing yet? Same point. I like that we can just keep accumulating all these data points, though. Sorry, you heard my reply, right? Or do you want me to reply to the email? There we are. Nice graph. See what this does. Be right back. The restroom. Or Hmm. Okay. Well, not doing better on sample F or anything yet, but doing experiments. $3 million for a solve is kind of, you know? Got way better before, though. Actually, how did I get way better? I parameterized more crap, didn't I? Yeah, this is about what it was. So, I mean, we'll see if this solves anything, right? Am I logging this correctly, actually? Yeah, am I logging this correctly? Think I am. Yeah, I'm pretty sure I am. So, I don't know why the discrepancy, but we can just run it and see if it finds anything good. And there's several things to be fair I probably wasn't keeping super good track of. Go take a look. On this one here, best we were getting was, we do have a 1 mil solve. Okay, we do actually have several 1 mil solves on this. They're slower, but they are solves. A little slower even. 26, not 27. I'm not dumb, right? You can just pick any of these, right? Good. That frame skip of 8. D4Ms. It could just be the model size is not being populated yet, right? Oh, 512. Actually, that is a 512 hidden. Okay. Okay, so we have that could be a model scaling result potentially. It should find this, right? 30-second run. 5 million. Really 1 million. I suppose we'll find out. These things suggesting mediocre stuff. Well, I guess I've had to relaunch this with crashes a few times. A mil with 8 frame skip is still not great though, right? Like 8 mil. I mean, still, we're going to be able to figure out a lot of stuff from this if we can just get it to be reasonable enough. Oh yeah, there we go. There's a whole bunch of runs, right? Still, this is the best thing up here. Mills. Why are we not getting like 1 million step? That kind of weird. Not getting 1 mil steppers. Seven. I am actually starting to wonder here, because like the min is at 900k. Is that right? Something's weird with that. 25 is 100k. So agent steps, the agent steps. Where do we get total time steps from, actually? I should be able to get, like, agent steps on -1, right? See if this changes it. Did that just change it, or did I just get this point? I think I just got this point, right? Let's go double check. Oh no, it's different. Okay. So somehow we are recording agent steps wrong on this other thing. Oh, because it doesn't take into account the timeout, I suppose. Yeah, that would be it. Okay. Well, there we go, right? There's our 1 million step 20 score run in no more than 30 seconds, I might add. So, that's pretty good. Anything else to add to this, I suppose? I don't think there's anything else to add to this. Pretty much exactly what I wanted. Well, I guess just that I can keep it running and we can see if we get anything lower. It is a little sus though that it's not running. It should be able to run sub millions. I guess we'll see if it decides to do that. But I mean, that's the key thing. This is all I needed, right? This was all I expected out of this, was being able to get this run. I should definitely commit this while I'm ahead. And then I'm gonna go for dinner, I think. I guess what I'm gonna do is I'm gonna let this run over dinner. And I think after dinner, I'm gonna re-queue this with no frame skip. I think that's what I'm gonna do. Because in the original, like, they count frames against you in that way. So we'll do it with no frame skip and we'll see. And actually, anything under 8 million means it's better than this, technically. So we can definitely get under 8 million with no frame skip, like guaranteed, right? So that's just a pure win, no downside. Pretty much guaranteed. Go. We're good, right? Funny that you only get these like 1 point, but okay. I mean, there's so much stuff we're going to be able to do with data like this. We've confirmed that the sweeps are fine, at least for this objective, right? We've confirmed the multi-sweeps are good. It's going to take some fiddling for sample F, but like, yeah, this is in a way, way, way better spot. Do I want to queue this on breakout? I think I kind of do, right? Sweep. This. This. What do we think about this? I think this is good, yeah? Except for this max cost, which we'll do 120 on. A 4x increase, I suppose. 180. Give it a lot of time, relatively speaking. See what we find out of this. Interested to see what comes of this. Oh, yeah, that looks working. See how it goes. Cool. That's 12 GPUs running on Puffer stuff. So, cool, right? 13, actually. Still have this other thing going. And, like, actually, this stuff has gotten way faster, right? With the changes. Um, this is like, that's clean. Yeah, this max cost thing and these longer evals made a huge difference. Our algorithm is actually better than I gave it credit for. It was just like the circumstances around it, the usage of it. And like the details of Pong as an env and stuff. No big deal. Okay. Well, I'm gonna call it there, folks. I will be back tomorrow. I'm gonna go get dinner. Why the heck does my restream crash? Okay. For folks watching, all my stuff's on puffer.ai. You want to help me out for free? Start the GitHub. Really helps a lot. If you want to get involved, join the Discord. And other than that, if you want to learn more about RL or get the latest from me, it's all on X, including my guides. There's going to be more sporadic science, I suppose, about the next few weeks, I'd say. And then once I get back to Maryland, that's probably going to be when the next big block of stuff goes, depending. I actually have no idea how hard this stuff is going to end up being. I think once we get this into place, it's not going to be that hard, but who knows. All right.